let's look at this example to see how A star works. First, this is a weighted graph. So I think in our actual credit, these are places at UCSD. This may be EBU 3B. This is our CS department. This may be Warren, whatever. So these are kind of different landmarks at UCSD. And we know there is a distance, right? There's a distance in between every one of them. We can assign heuristic to each of these vertices. So supposedly our source is V0. This is our source. Our target is T. So we're trying to go from S to T. What is the shortest path that leads from S to T? The heuristic, you can say, is always the distance, the direct line distance between a node to T. So for example, the direct line distance from V2 to T is, in here it is given as 9, but you may not know that in a given data set. So basically these heuristics, they are kind of the direct distances between a certain vertex to T. So basically it's the distance between V0 and T. This is the distance between V1 and T and etc. Right, so you can use this Euclidean distance between this vertex and the target as your heuristic. And this one is guaranteed to be both admissible and consistent. As for why that's the case, you can go to Wikipedia. It's kind of explained fairly clearly over there. Okay, so let's kind of run A star a little bit here. So we have the starting point S. If you look at the nodes in here, you have for each node you have the dist, you have the heuristic. The heuristic is fixed, and then we are looking at the sum of the dist with heuristic, and this is the node that this is the value that we will be using as the priority in the priority queue. We still have the previous for the path, we still have done, so just like before. The only difference in here is the value in there. All right. So in the beginning, I'll draw the queue over here up on the top, so you can see it clearly. In the beginning, we'll say v dot dist is 0. The distance, the heuristic is 7, so v dot dist plus hv equals to 7. And we unqueue it, 7 v0. So we unqueue that. And then we start the dequeuing process. We pop this. So once you pop a node, it is done. We look at all the neighbors of V0. We have V1 and V2. If you look at the triangle inequality for Dasher, V1, the dist is updated as 1, previous is updated as 0, right? So it's going to come from V0. And at this time, we can also update the v.dist plus hv, which is basically what people usually refer as f. Okay, so the f value now changing to 7 because you updated the f value, so you will unqueue v1. And in fact, because the heuristic is fixed, at least in our example, so when you update v.dist, you are basically updating the heuristic plus v.dist. So we're going to unqueue 7v1 in there. Similarly for v2, this one is updated as 4. And if you add 4 with 4, you get 8. Previous changing into 0, and we unqueue 8v2. Okay, so those are the two neighbors of v0. Now we dequeue based on f value, which is what we just having here. So it's 7v1 v1 is out, so it's not true. We will look at the neighbors v1. We have v2, v3, and t. So we look at v2. If you look at the distance for v2, it used to be 4, but right now it's v1's this, which is 1 plus 2, that's a 3. So we get better in here. And this one changing into 7. So we're gonna unqueue 7 v2 in here. And obviously the previous is changing into 1. For v3, right now it's infinity. We go from v1, which gives us 6. You add 6 with 2, you get 8. And this previous changing into 1, you unqueue it, so it's 8 v3. We also have t. This is our target. You only say, well, I've reached the target when you pop a node with the target in there. That's when you say the search is done. Right now, we have we are looking at v1 as of now. So it's 1 plus 8, which is 9 in here. 9 plus 0, which is 0. You may ask, why is it 0? Because if you use the direct line distance between t and t, it's going to be 0. So this one will be 1, and we unqueue 9 t. Okay. So we are done with all the neighbors v1. Now we'll dequeue the next one, which is the smallest, which is v2. So v2 is done. v2 is done. We look at all the neighbors of v2. We have v3 and t. For v3, if you look at v3's current value for this is 6. v2 is 3. The distance between v2 and v3 is 2. So 3 plus 2 is 5. So we have an update over here. And this one is updated to be 7. This one is updated to be 2. Because there is an update in here, we will unqueue v3 in here. For t, v2's distance is 3. 3 plus 9, which is 12. 12 is no better than 9, so we don't update t. And now we are done with all the neighbors of v2. Now we will pop again, which is 8 v2, because v2 is already visited, so we just ignore it. The next thing we say is 8 v3. So if you look at the neighbors v3, so v3 now is fixed. v3 is true. We look at all the neighbors of, no, sorry, we are not looking at 8 v3. We are looking at 7 v3. Okay, this is what we pop. But at this time, v3 is true. We look at the neighbors v3, it is only t in there. And if you look at the distance for t from v3, which is 5 plus 6, which is 11, is not better than t. So we don't update it. And then we pop 8 v3. v3 is already visited, so we don't worry about it. The last thing is 9t. For 9t, what we have in here is t is the target. We already reached it. So the smallest distance from v0 to t is 9. And if you look at the path, we have, which is this path up there. So this is what A star does. The major difference in here, although in this example you may not be able to see kind of why it is better, but if your graph is more complicated, using this heuristic, this HV, will allow you to guide towards this T in this direction instead of being divergent to the other places. All right, I hope this video is helpful for you to do the extra credit for PA4. Good luck.